This is number 17 from the Anton book. A 13-foot ladder is leaning against the wall. If the top of the ladder slips down the wall at a rate of 2 feet per second, how fast will the foot be moving away from the wall when the top is 5 feet above the ground? So first of all, I'm going to show you the calculus of it as I drew it here with my lovely diagram. Then we're going to go through the calculus first, but then I really want to build a simulation so that you get a better idea of what's going on, especially as we take the derivative with respect to time. So looking at it from the idea of implicit differentiation, we have x squared plus y squared equals 13 squared. So what we're saying here is that y is going to change and x is going to change, but because it's a ladder, the 13 doesn't change. So when we take the derivative of both of these processes with respect to time, we have 2x dx dt plus 2y dy dt equals 0, because 13 squared is a constant, so the derivative of a constant is 0. So then when I solve for dx dt, because we want to solve for the rate at which the foot is moving away, that's dx dt. So we want dx dt when y is 5. So dx dt, just doing algebra, is negative 2y over 2x times dy dt. And when you put in all of your numbers and variables, you get 5 feet over 6 seconds, or 6 feet per 1 second. Okay, so that's the calculus. Now let's talk about what's really going on here. Imagine that you've got, this is the ladder here, and this is y, and this is x. What we see when it's a related rate is that, notice I'm moving the time down here. In other words, time is marching on and that baby's falling down. Well, it can't fall farther than in real life, right? It can't fall farther than 0, but this is math and we can do whatever we want to extend reality. So I'm going like this, and what we want to do is we want to look at the rate of change of x and y with respect to time. So I want to put them both on a graph where the horizontal, or the x, is actually time. So let's go ahead and do that. We're going to say, first of all, this is y of t. Now, the fact that it looks like the ladder has nothing to do with it, because the real issue is that each value, each e value here, says that at this time, 1.19 seconds, it is 10.63 feet high. Okay? As time goes on, let's say at 2.58 seconds, it's 7.85. So this distance here, if I were to measure it, it would be, oops, I got too much selected here, but if I measure this distance, it's 7.85. Now, I use centimeters, obviously, instead of feet, because it wouldn't fit on my diagram here. But notice how these two numbers are always the same, because what we're looking at is the rate of, well, we're looking just at the height right here of y, okay? I could actually do this. I'm going to say y is equal to this right there. For those of you who have Sketchpad, notice that you can make an interactive, okay? You can make an interactive diagram there, so it's really kind of nice. You can see how these two numbers always stay the same. Now we know how y is changing, and we know that it's a constant at -2, because the slope of this is -2. Now the question is, we want to know dx dt. So the next thing we want to do is to find an expression for x in terms of time. Well, we did that. We solved for x, and we found that it's 13 squared minus y of t squared. So this is actually y of t, because this is the value of y at any point t. So this is now dependent on time. So x of t is also dependent on time, because it's dependent on what y is. So now again, as we move this, okay, there's going to be a corresponding value for each time for each x value. So as a matter of fact, you can see right about here, this is an equilateral triangle right there, right? 9.32, and this is also 9.32. This x value, the purple. I should probably make this purple. That would be cool, so that you know that this is purple. But now those two, this shows you how this is. And so it's interesting because you might think that if time is going at a constant and y is changing at a constant, that x would be changing at a constant. But it doesn't. It changes, it starts changing fast and then it goes slower. So we want to know, so in general, right, here is the tangent line. This represents the rate of change of x. And you can see the slope is very, very steep here, so it's changing really fast here, but then it kind of slows down. So even as time is marching on, the foot goes much faster at first than it does later on, and that is beautiful mathematics. So the final thing is to show, well, what is happening when it's 5 feet above the ground. So I'm going to show x of t here. This is 5. So I just line this up and they say, aha, it's right there. And it looks like it's about when the time is about 4. And notice the slope of the tangent line here is 0.83, which is 5/6, which is what we got when we did the calculus. So I hope that this has been helpful in understanding a little bit more of how you're taking both x and y with respect to time.